Size exclusion chromatography (SEC) is also known as gel exclusion chromatography or molecular exclusion chromatography or gel filtration chromatography. SEC is a versatile chromatographic technique that is widely used to separate molecules based on their size by filtration through a gel. Unlike techniques such as ion exchange chromatography or affinity chromatography, molecules do not bind to the chromatography resin, which means that the powerful composition does not directly affect resolution, the degree of the separation between peaks. And the gel consists of spherical beads containing pores of a specific size distribution dependent on the nature of the particle making up the gel. Therefore, SEC has an advantage where the condition can be varied to suit the type of sample or the requirements for further purification, analysis, or storage without altering the separation.
SEC is a type of liquid chromatography, which means that a liquid mobile phase is used to move the sample through the system. As such, the technique requires that the sample be wholly dissolved into a solution before injection. A standard list of supplies for sample preparation includes a simulation vial, a balance, a method of dispensing a known volume of dissolution solvent, a way to introduce gentle agitation to facilitate the solution, a lure lock syringe, and a syringe filter. The preparation method described here is applicable to both manual injector and auto-sampler systems. This demonstration will place the final sample solution into an auto-sampler vial. The first step is to weigh the sample into the simulation vial. This way, if complete dissolution occurs, the sample concentration will be known. Knowledge of the sample concentration allows you to calculate the sample DNDC value, which ensures accurate data calculation and obtains additional information such as percent recovery. The second step is to dilute the sample with the dissolution solvent. The dissolution solvent is often the same as the mobile phase and can be drawn directly from the mobile phase reservoir. This will help minimize solvent mismatch peaks in the chromatograms. In some cases, the dissolution solvent is different than the mobile phase. That is okay as long as the sample will remain in solution in the mobile phase once the dissolution solvent has been separated away. Since the mass of the sample is known, it is important to use a pipette or other graduated liquid dispenser to add a specific volume of dissolution solvent so that the exact concentration of the sample and solution can be determined. Next, dispense the dissolution solvent into the simulation vial containing the sample and secure the cap. Third, apply the gentlest conditions possible to facilitate the complete dissolution of the sample. This can be done by simply letting the sample solutions sit on the bench at ambient temperature or applying gentle agitation with a shaker, rocker, or rotator. Temperature is another way to encourage dissolution. If heat is applied to a sample, it is recommended to use the minimum temperature and time required and to combine it with gentle agitation to minimize any potential sample change or degradation. It is also important to check that the sample will remain in solution when cooled down to either ambient temperature or the temperature of the autosampler columns and detectors. Let the sample dissolve for an adequate amount of time. A good rule is to wait an extra hour after it appears to have completely dissolved. Periodically examine the sample solution to make sure the sample is not stuck to the side of the vial or has begun to gel instead of dissolve. Now that you have a homogeneous sample solution, the last step is to filter it. It is important to use a syringe and a syringe filter that are compatible with your sample solution. For example, do not use a syringe with a rubber tip plunger when working with organic solvents. Regarding the filters, we recommend filtering all sample solution through a syringe filter with 0.2 micrometer pores. These syringe filters are available with nylon membranes for general aqueous sample solutions, PTFE membranes for organic sample solutions, and cellulose acetate membranes for aqueous protein solutions. If you are using an autosampler, you can filter directly into autosampler vials. This will remove any insoluble material or other particulates that can damage the instrument column and detectors.
Let's delve into the key component and steps that constitute the SEC process. Firstly is a column. At the heart of SEC lies a specialized column filled with the porous beads. These beads possess a specific pore size distribution crucial for determining the range of molecular sizes that can be effectively separated. The column serves as the medium tube which our sample component will traverse. Second is mobile phase or eluent. A continuous flow of a mobile phase, typically a buffer solution, is maintained throughout the column. This mobile phase facilitates the movement of the sample component, allowing them to journey through the column in a systematic manner. Next, sample application. Our sample, which could encompass a mixture of molecules with a varying sizes, is introduced at the top of the column. This sample is carried along by the mobile phase, initiating its passage through the bead-filled column. After that is separation. The magic of separation unfolds as the sample moves through the column. Larger molecules, unable to penetrate the pores of the beads, take a more direct route, eluting more quickly. On the other hand, smaller molecules navigate the intricate path within the beads, resulting in a longer elution time. This fundamental principle, separation based on size, is the essence of the SEC. Next, we move to the detection. As the separated component exit the column, they undergo detection. Various detectors such as UV visible spectrophotometers or refractive index detectors come into the play, depending on the nature of the molecule being analyzed. Lastly is data analysis. The data obtained from the detector is transformed into the chromatogram, a graphical presentation of the separation process. Peak of the chromatogram signify distinct molecule entities, with their position corresponding to the size or molecular weight of the sample component. To unlock the molecular secret within our sample, we measure the elution volume. By comparing this data to the calibration curve established using the known standards, we can precisely determine the molecular weight or size distribution of the sample component.
Next, the principle of size equation chromatography (SEC). SEC, also known as a gel filtration chromatography or gel permutation chromatography, is a technique used in analytical chemistry for separating and characterizing molecules based on their size. It operates using a specialized chromatographic column filled with porous materials like polymeric gel or agarose bead, which generally ranging from 10 to 40 micrometer in diameter. This porous material acts as a stationary phase. The mechanism relies on the principle of trapping smaller molecules within the pores of this material, while allowing larger molecules to circumvent them as they are too large to penetrate the pores. Because of that, larger molecules proceed through a column swiftly and experiencing shorter retention time, whereas smaller molecules navigate the convoluted path through the pores, resulting in longer retention time. To conclude, SEC cross principle is succinctly captured that the size of the molecule directly influences its retention time within a chromatographic system.
Size exclusion chromatography is a chromatographic technique used for the separations and analysis of macromolecules based on their size. This method is particularly useful for biomolecules such as protein, nucleic acids, and polysaccharides. Here's a brief explanation of its main application. First, the procedure involves desalting, which means extracting inorganic salts from a liquid containing biomolecules. Size exclusion chromatography facilitates desalting by exploiting difference in molecular size. In this chromatographic technique, a porous column separates molecules based on their ability to enter pores in a gel matrix, with smaller molecules having a longer path through the column. When applied to a liquid containing biomolecules and inorganic salts, the salts smaller enter the pores and elute later, while larger biomolecules pass through the column more quickly, resulting in their earlier elutions. Consequently, the final elution fractions collected from the sac column contain desalted biomolecules, making it an effective method for the removal of inorganic salts from a liquid sample containing biomolecules of interest. Next, another main application of size exclusion chromatography is characterizing polymers by determining their molecular weight. Size exclusion chromatography helps determine the molecular weights of polymers. It works by separating polymers based on their size, with smaller ones taking out longer to come out of the column and the larger ones eluting earlier. By comparing the elution times of a polymer sample to standard with known molecular weights, you can create a calibration curve. This curve allows you to figure out the molecular weight of the polymer you are studying. Essentially, SAT is a useful tool for understanding the size distributions of polymers, which is important in various applications.